Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at a Mathematics Olympiad question. This was suggested by a viewer. So the problem is let a, b and c be rational numbers such that a plus b cube root of 2 plus c cube root of 4 equals 0. We're required to prove that a equals b equals c equals 0. So first let's set up some notation. Notation is so important in mathematics. So first we write cube root of 2 as alpha. This means the cube root of 4 is the cube root of 2 squared is alpha squared. So the original equation becomes a plus b alpha plus c alpha squared is 0. Now if we can show that 1 alpha and alpha squared are linearly independent over the rational field, then this means that the values of a, b and c are unique, and given that we have a solution a equals b equals c equals 0, that's the unique solution, so they all must be 0. So we need to show these three are linearly independent. So I'm going to demonstrate two methods. One of them is based on kind of university mathematics and one of them is more elementary. Of course, the participants in the Olympiad are pre-university, so it's good to have an elementary solution as well. But this university level one is nice because it's conceptually very insightful. So Q of alpha is a field and it's an extension of Q, which is the field of rational numbers. X cubed minus 2 is the minimal polynomial of alpha. We can show by Eisenstein's criterion that x cubed minus 2 is irreducible over the rational field. So the point is that 2 is a prime number, 2 divides all of the coefficients except the leading one, and 2 squared does not divide the constant term. So this shows that the polynomial is irreducible. The polynomial has degree 3, and so the extension has degree 3. Alpha and alpha squared are roots of the minimal polynomial, and so 1 alpha and alpha squared constitute a basis of the extension field when it's considered as a vector space over Q. So that means that 1 alpha and alpha squared are linearly independent, and so indeed a, b and c must be 0 because the solution a equals b equals c equals 0 is the unique solution. But we also, as I said, have this elementary proof. So to obtain a contradiction, let's assume that in the equation that we have, c is not 0. So in this case, we subtract a from both sides, we subtract b alpha from both sides, we divide by c, and we get alpha squared equals minus a minus b alpha over c, which we're going to write as p plus q alpha. And we can rearrange this as alpha squared minus q alpha minus p equals 0. But then alpha satisfies a quadratic equation. Now this cannot be the case because we know that alpha satisfies the cubic, x cubed minus 2 equals 0. And so therefore it can't satisfy a quadratic because this cubic was irreducible. And so that means that c must be 0 because saying that c is not 0 creates a contradiction. So now we have a plus b alpha is 0. If we assumed b was not equal to 0, then alpha would be minus a over b. But we know alpha is not rational because we can prove the cube root of 2 is not rational in the same way we can prove the square root of 2 is not rational. So that means b must be 0, and if c and b are both 0, then we just got a is 0, so they're all 0. So that's really nice. We've got two different proofs that a equals b equals c equals 0. And then next, we've shown using Eisenstein's criteria that x cubed minus 2 is not reducible. But just to reassure ourselves, especially for the constructive instincts within all of us, let's look at how this actually factors within the real number and the complex number fields, and that will let us know why it is irreducible in the rationals. So the first thing is, we're going to refer to the cube root of 2 as alpha, then we know that x minus alpha is a factor of x cubed minus 2, and then we can do some polynomial division in our heads, and we basically get x cubed minus 2 is x minus alpha times x squared plus alpha squared. If you want to check it, let's check it. X times x squared is x cubed, all good. Then let's look at terms in x squared. You get x squared times minus alpha x squared. Then you get alpha x times x plus alpha x squared, they cancel. Let's look at linear terms. X times alpha squared here, and then here you've got minus alpha times alpha x is minus alpha squared x, they cancel. And then you've got minus alpha times plus alpha squared minus alpha cubed is minus 2. So that shows why this factorization works. The discriminant of the quadratic term is b squared minus 4ac, which is alpha squared minus 4 alpha squared, always going to be negative, minus 3 alpha squared. So actually what we've got is two complex roots. So we can use the equation minus b plus or minus square root of b squared minus 4ac over 2a. And what we get is minus alpha, which is minus b, plus or minus square root minus 3 alpha squared over 2. So actually what you get is the three roots being the cube roots of unity times by alpha. So this is going to come out as minus alpha plus or minus I times the square root of 3 times alpha over 2, which is just these two cube roots of unity times by alpha. And then the other one is just alpha, which is just 1 times alpha. And it sort of makes sense that the three roots would just be, because basically x cubed minus 2, it makes sense that the three roots of that would be the cube roots of unity multiplied by the cube root of 2. And that shows us why this is not reducing in the rational field, because alpha is not rational and these two are complex numbers. I mean, as it happens, they also have an irrational component, but they're fundamentally complex numbers, so it's not going to factorize in the rational field. Thank you. I hope you like this video. Please do like it if you do. Please subscribe and hit the notification bell. I'd love to hear your ideas, and most of all, I hope you enjoy your mathematics.